Chaos, Making a New Science by James Gleick. Picture this. It's 1974 in Los Alamos, New Mexico. Night after night, local police notice something odd. A man wandering the dark streets for hours, the faint glow of his cigarette tracing invisible patterns in the darkness. He's not going anywhere in particular, just pacing, lost in thought. The police had no idea they were watching history unfold. This wasn't some restless insomniac or suspicious character. This was Mitchell Feigenbaum, a physicist wrestling with a problem so profound it would spark the third great revolution in 20th century physics, right up there with relativity and quantum mechanics. That problem? Chaos. Today we're exploring James Gleick's fascinating book, Chaos, Making a New Science. This isn't your typical dry science text. It's the story of brilliant rebels who looked at the messy, unpredictable world around us. Turbulent waterfalls, wild stock market swings, irregular heartbeats, and discovered something everyone else had completely missed. They found hidden order. For centuries, science had one clear goal: find simple, predictable laws. Newton gave us a clockwork universe where knowing the starting conditions meant you could predict the future with perfect accuracy. It was beautiful, elegant, and completely inadequate for explaining most of reality. How do you use perfect circles and smooth curves to describe a jagged coastline? What equations capture the intricate dance of smoke rising from a candle? These messy, irregular phenomena were dismissed as noise, random exceptions to the clean rules scientists preferred. This book tells the story of the Mavericks, who looked directly into that noise and discovered a completely new kind of order, universal laws governing complex behavior in everything from weather patterns to the deepest rhythms of life itself. By the time we're done today, you'll understand the butterfly effect and how a butterfly's wings really can influence a hurricane halfway across the world. You'll encounter fractals, the breathtaking geometry that nature uses to build itself. Most importantly, you'll discover that beneath the apparent randomness of our world lies something profound and elegant, a hidden structure connecting everything together. This isn't just a book summary, it's an invitation to see the world with completely new eyes. So let's dive in. Our story begins in 1961, not in some prestigious laboratory, but in a cluttered MIT office. Edward Lorenz, a meteorologist, hunches over a primitive computer called the Royal McBee, basically a tangle of vacuum tubes and wires. He's running an absurdly simplified model of Earth's weather. No clouds, no seasons, just a few basic equations describing wind and temperature. Every minute, the machine spits out a new line of numbers representing another day in this artificial world. Lorenz watches digital storms spin across his imaginary globe. What fascinates him is that the weather never repeats exactly. It has patterns, sure, but they're constantly shifting, always creating something new. Despite the simplicity, it felt remarkably real. One day, Lorenz wants to examine a particular weather sequence more closely. To save time, instead of restarting the whole simulation, he decides on a shortcut. He types in numbers from an earlier printout to give the machine its starting point, then heads down the hall for coffee. When he returns an hour later, he sees something that should be impossible. The new printout should match the old one perfectly. The computer was deterministic. Same input should always produce identical output. But the patterns had diverged. They started out nearly identical, but within a few simulated months, all resemblance vanished. It looked like two completely different weather systems. His first thought, vacuum tube failure, but then the truth dawned on him. There was no malfunction. The problem was in the numbers themselves. You see, the computer stored numbers to 6 decimal places internally, something like 0.506127. But the printouts, to save space, only showed 3, 0.506. Lorenz had entered the shorter number, assuming this tiny difference, 1 part in 1,000, was completely insignificant. This was fundamental scientific dogma since Newton, tiny disturbances create tiny effects. If your initial measurement is slightly off, your prediction will only be slightly off. This principle is what lets us guide spacecraft and predict comet returns with stunning accuracy. But Lorenz's computer was screaming something different. In his system, that microscopic difference didn't stay small. It grew, cascading through the equations, until it completely transformed the future. He'd discovered what we now call sensitive dependence on initial conditions. The implications were staggering. For complex systems like weather, long-range prediction wasn't just difficult, it was fundamentally impossible. Even with a perfect weather model, the tiniest measurement error, a temperature reading off by a fraction of a degree, a wind speed slightly misjudged, would eventually explode until your forecast was worthless. This became the famous butterfly effect. The idea, only half joking, is that a butterfly flapping its wings in Beijing today could genuinely transform storm systems in New York next month. The system is so sensitive that the smallest perturbation anywhere can create massive consequences elsewhere. For most people, this discovery would be devastating news. It revealed hard limits on human knowledge. But Lorenz was a mathematician at heart, and he saw something more beautiful hidden inside this unpredictability. He simplified his weather model down to just 3 elegant, non-linear equations. When he plotted the system's behavior in what's called phase space, something magical appeared. The trajectory didn't fly off randomly into infinity, nor did it settle into a boring, repeating loop. Instead, it traced an elegant, infinitely complex shape, a double spiral resembling butterfly wings. The path never repeated itself and never crossed itself. It was an infinitely long line somehow contained in finite space. This was order disguised as randomness. The shape became known as the Lorenz attractor, the first strange attractor ever discovered, a portrait of chaos itself. It showed that even simple, deterministic systems could produce behavior that was endlessly creative, complex, and beautiful. Lorenz had opened a door, but for years, almost nobody walked through it. His paper appeared in a meteorology journal in 1963, and the physics world, obsessed with the clean predictability of subatomic particles, simply wasn't ready. The scientists who would eventually build chaos theory were scattered across disciplines, working in isolation, often completely unaware of each other. They were rebels examining the noise and messiness their colleagues were trained to ignore. One of these rebels was the brilliant, eccentric Mitchell Feigenbaum at Los Alamos. In 1975, armed with nothing more than a programmable calculator, he started playing with a deceptively simple equation ecologists use to model population changes. The equation was a feedback loop. Take a number, plug it into the equation to get a new number, then plug that result back in, over and over. He was fascinated by what happened when he adjusted a single parameter controlling how boom and bust the system behaved. At low settings, the population settled to one stable value, but as he turned up the dial, something strange happened. The stable state split in two. The population began oscillating between two different values instead of settling down. He increased it further. It split again into 4 values, then 8, then 16. This was a period doubling cascade. The splits came faster and faster. Feigenbaum meticulously calculated the exact parameter value triggering each new split and noticed something astonishing. The numbers converged at a constant rate. There was a universal pattern in the system's descent into chaos. He calculated this convergence rate as precisely as he could. The number was 4.669. Now he wondered if this was just a fluke, a quirk of this particular equation. So he tried a completely different one using trigonometric functions. He recalculated the entire period doubling sequence from scratch. Once again, he saw the same geometric convergence. He calculated the ratio. It was 4.669. The exact same number, from completely different equations. This was electrifying. It meant there was deep universality in how systems become chaotic. The specific details, Whether you're modeling fish populations, fluid dynamics, or financial markets, didn't matter. The route to chaos followed universal laws, governed by this new fundamental constant of nature. Feigenbaum had discovered that chaos itself was orderly. But was this just mathematical curiosity, or did it apply to the actual physical world? That question was answered by Albert Liebschaber, a quiet, ingenious experimenter in Paris. In 1977, Liebschaber built a tiny apparatus he called helium in a small box. At its heart was a cell no bigger than a lemon seed filled with liquid helium, heated from below and cooled from above. This was a physical version of the convection system Lorenz had modeled. With extraordinary precision, Liebschaber carefully increased the heat, creating two tiny rolling cylinders of fluid. As he raised the temperature further, he watched the flow become unstable. A wobble appeared. Using microscopic probes to measure temperature, he observed the oscillations. Then, exactly as Feigenbaum's theory predicted, he saw period doubling. A rhythm at one frequency was joined by a new rhythm at half that frequency. Then, a quarter. Then, an eighth. The abstract numbers from pure theory were appearing with stunning precision in a real physical system. This was confirmation that universality wasn't mathematical abstraction. It was a genuine law of nature. The experiment was a masterpiece, elegantly bridging the abstract world of equations and the tangible world of matter. While Feigenbaum discovered universal rules governing time, another scientist was discovering the universal geometry of space. His name was Benoit Mandelbrot. Mandelbrot was an intellectual nomad, wandering between economics, linguistics, and physiology, always hunting for patterns others missed. He was a geometer who thought in pictures rather than equations, and he was haunted by one question: what is the shape of nature? Classical Euclidean geometry is a world of smooth, perfect forms, lines, circles, spheres, cones. But, as Mandelbrot liked to say, clouds are not spheres, mountains are not cones, coastlines are not circles, and bark is not smooth, nor does lightning travel in a straight line. Nature is rough, jagged, and complex. Mandelbrot sought a new geometry to describe it. He stumbled upon a paradox with a seemingly simple question: how long is the coast of Britain? The answer, he discovered, depends on your measuring stick. Measure with a yardstick, you get one answer. Use a 1-foot ruler, you'll capture more nooks and crannies and get a larger number. Use a 1-inch ruler, the number grows even more. As your ruler shrinks, the measured coastline length grows toward infinity. This paradox led to a revolutionary idea: fractional dimensions. A jagged coastline isn't a simple one-dimensional line. It's more than a line, but less than a two-dimensional plane. Its dimension is a fraction between 1 and 2, and that number precisely measures its roughness. Mandelbrot named this new family of shapes fractals. A fractal is self-similar. Zoom in on any small piece, and you see structure resembling the whole thing. The pattern repeats at every scale, from macroscopic to microscopic. Think of a fern. The entire frond consists of smaller fronds, each made of even smaller ones. Or a tree. Trunk branches into limbs, limbs into branches, branches into twigs. This is nature's geometry. Blood vessels, snowflakes, river networks, galaxies. Mandelbrot found fractal patterns everywhere. The most famous fractal bears his name, the Mandelbrot set. Generated by a simple iterative process with complex numbers, it produces breathtaking, infinite complexity. It's a bug-like shape, a black continent studded with smaller copies of itself. Zoom in on its boundary, and you discover an endless universe of spirals, filaments, and seahorse tails. Every part, however tiny, contains intricate detail, always similar, yet never exactly the same. It's mathematics, most complex object, yet generated by one of its simplest rules. The Mandelbrot set became an emblem for chaos theory. It visually demonstrated how simple rules, repeated endlessly, generate infinite complexity. It was the geometry of the butterfly effect made visible. By the late 1970s, the revolutionary pieces were coming together. At UC Santa Cruz, rebellious graduate students calling themselves the Dynamical Systems Collective, or the Chaos Cabal, began synthesizing these new ideas. Led by visionary Rob Shaw and energetic Doyne Farmer, they used forgotten analog computers to explore strange attractors. They saw chaos not just as a limit on prediction, but as a source of creation. They connected chaos to information theory, arguing that chaotic systems constantly generate new information because of their unpredictability. A simple periodic system like a pendulum clock quickly becomes boring. Once you know its rhythm, that's everything. But a chaotic system like a dripping faucet is eternally creative, its drip pattern never repeating. Shaw saw this as a bridge between the microscopic world of random molecular motion and the macroscopic world we experience. In chaotic systems, tiny uncertainties from the microscale are amplified, bubbling up to create visible, unpredictable behavior at the macroscale. Chaos, he argued, was nature's mechanism for creating information. These young physicists started seeing chaos everywhere, in flapping flags, rattling car fenders, irregular heartbeats. They developed techniques to analyze real-world data, taking seemingly random number streams and reconstructing the strange attractor hidden within. This powerful new tool meant scientists in any field, biology, medicine, economics, could search for deterministic chaos underlying the complexity they studied. And that's exactly what started happening. Biologists and physicians began discussing dynamical diseases, disorders caused not by broken parts but by breakdowns in the complex rhythms governing our bodies. The most dramatic example was the heart. A healthy heart doesn't beat with machine-like regularity. Its rhythm has subtle, healthy variability. Researchers like Ari Goldberger at Harvard Medical School discovered that in some heart diseases, the heartbeat becomes too regular. The system loses flexibility and adaptability. It locks into simple, periodic rhythm. This loss of complexity can precede catastrophic failure, ventricular fibrillation, where heart muscle tissue quivers uselessly in lethal chaos. In this new view, chaos wasn't purely disease. Paradoxically, certain kinds of chaos signaled health. Healthy systems are complex and adaptable, with rich spectrums of rhythms. The body, like weather, seems to thrive at the edge of chaos, that fertile region between rigid order and random disorder. Life itself appeared to be a balancing act on this creative frontier. From a simple discovery in a meteorologist's office to a new geometry of nature and a revolutionary understanding of life, chaos theory had redrawn our map of reality. It showed us the universe isn't a sterile, predictable clockwork. It's a place of endless creativity, surprise, and beauty, where simple rules birth infinite complexity, and within chaos's heart lies unexpected and profound order. After finishing a book like Chaos, the world shifts slightly. You start seeing patterns everywhere. A meandering river reminds you of the arteries in your body. Smoke breaking into wild swirls makes you think of the butterfly effect. James Gleick didn't just write about science. He gave us a completely new lens for seeing reality. The most powerful lesson for me is the profound relationship between simplicity and complexity. We're taught that complex outcomes require complex causes. If something behaves erratically, we assume countless complicated forces are at play, or it's just random noise. But chaos teaches the opposite. The most intricate, unpredictable, beautiful patterns in the universe can arise from the simplest rules, repeated over and over. The Mandelbrot set, born from one simple equation, is the ultimate proof. This idea resonates philosophically. It suggests that life's complexity, the intricacy of our minds, the vastness of the universe, none of it might be as hopelessly complicated as it seems. There might be simple, elegant principles working beneath the surface, if we learn to see them. Another key insight is the humility this science inspires. For centuries, science's dream was total prediction and control. French mathematician Laplace, once imagined an intelligence knowing every particle's position and momentum in the universe. For such an intelligence, he wrote, nothing would be uncertain, and the future, as the past, would be present to its eyes. Chaos shattered that dream. It revealed that even in perfectly deterministic worlds, there are fundamental limits to knowledge. The butterfly effect isn't just clever metaphor, it's a real boundary. But this isn't pessimistic, it's liberating. It replaces the cold, mechanical clockwork universe with something far more organic, creative, and alive. It tells us the future isn't just a predetermined script playing out. It's open, full of surprise and possibility. So how can we apply these profound ideas to our own lives? First, learn to appreciate the, quote, orderly disorder around you. Next time you see a jagged coastline, turbulent stream, or intricate tree branches, don't just see messiness. See a fractal. See a physical manifestation of deep mathematical truth about how nature builds things. This perspective shift can transform a simple walk in the woods into a profound experience. Second, embrace sensitive dependence in your own life. We often underestimate small changes, power, a tiny shift in daily habits, a single new idea you pursue, a brief conversation with a stranger. These small inputs can, over time, lead to vastly different outcomes. Chaos theory tells us these aren't just feel-good platitudes. They're fundamental properties of how complex systems work. Your life is a complex system. Small, consistent efforts genuinely create massive, unpredictable transformations. Finally, question the linear models we're taught. We expect a little more effort produces a little more result. We expect smooth, predictable change. Chaos shows this is often wrong. The world is full of non-linearities, sudden shifts, and phase transitions. Change can be abrupt and dramatic. Understanding this helps us prepare for sudden shifts in careers, relationships, and the world at large. It encourages flexible resilience, awareness that the ground beneath our feet isn't as solid as it seems. That was a summary of Chaos, Making a New Science by James Gleick. We've explored some incredible landscapes of this new science today, but I'll be honest, a summary can only guide you to the territory's edge. The real magic happens when you venture in yourself. It's in the quiet moments of reading, when a particular story or simple phrase ignites unexpected curiosity. This summary is a map to help you decide if this journey is for you. If anything we discussed sparked wonder, grab a copy of the book. Reading it isn't just about learning facts. It's an experience that can genuinely change how you see our beautiful, complex, chaotic world. A link to the book is in the description. Also, if you found this summary valuable, please like this video and subscribe to the channel. It tells us these journeys are worthwhile and ensures you won't miss our next exploration into another life-changing book. Let's keep growing together.